Welcome back to the deep dive. So let's picture this. You've made a massive investment in your manufacturing facility. We're talking cutting-edge equipment, like a medium speed wire EDM machine.
The MS-WEDM, yeah.
Mm,
A machine designed for, tolerances tighter than almost anything else you can buy.
exactly. You're making parts for aerospace, for medical, the high-value stuff. You spend a fortune on this tech, calibrate it perfectly, but then a few weeks later, the parts start coming out wrong.
And that's where the real frustration kicks in. Because the immediate reaction always is to check the software, maybe blame the operator for a bad parameter.
Right, you think it has to be some kind of high-tech failure inside the machine.
It's always the first assumption. But what we found in the source material for today's deep dive is that this assumption is almost always wrong.
It just completely flips it on its head. We're here to tell you that for MS-WEDM, the million-dollar problem often has a $1,000 fix. The real culprit isn't the code.
It's the room.
It's the room itself.
We've seen so many case studies. Factories spending a fortune chasing an electronic ghost when the real issue was, and I'm not kidding, an open loading dock door letting in a draft. Or a patch of morning sun hitting the machine frame.
So the environment isn't just the backdrop for the work.
No, it's an active, non-negotiable part of the machine system.
Okay, so that's our mission for today. We're going to cut through all that complexity and give you a clear guide on the four non-negotiable environmental requirements you need to get the performance you paid for.
We're talking temperature, dust, vibration, and air quality.
Yeah.
All these things that are secretly, conspiring against your bottom line.
So where do we start?
We have to start with the most subtle one the source material calls the silent killer.
Temperature control.
Exactly.
That sounds dramatic, the silent killer, but I get it. When your whole job is controlling movement down to a few hundredths of a millimeter, basic physics becomes your biggest enemy.
It really does. It's just basic thermodynamics. Metal expands when it's hot, contracts when it's cool. If your workshop temperature is all over the place during the day,
your cutting accuracy is just going to drift constantly.
Guaranteed. The source puts it perfectly. It says to think of your machine tool, even a massive iron one, like it's a living thing. It reacts to its environment.
And the core data point that I found just staggering was the required stability. The rule is the room has to be controlled at around 20 degrees Celsius.
Which is 68 degrees Fahrenheit, yeah.
But the killer detail is the fluctuation. It has to be kept under plus or minus 1 degree Celsius. That's an insanely tight window.
It's essential because heat doesn't just cause expansion, it causes uneven expansion. And that's where things get really bad.
What do you mean by uneven?
Okay, think about that huge multi-ton iron machine frame. If you have an unsealed window and sunlight hits one side of that machine for 2 hours in the morning.
So one side gets warm and the other stays cool.
Precisely. And that warm side expands while the cool side doesn't. The entire frame is now physically twisting ever so slightly.
And that has to throw the machine's axis completely out of whack.
Completely. The lead screws that move your X and Y axis, they expand. The workpiece itself expands. Suddenly the cut you calculated is just wrong.
And then there's the really high-tech part of it, the electrode wire.
Yes. That wire is incredibly sensitive. It's thinner than a human hair. Heat makes it sag or stretch, just a tiny amount.
But that tiny amount is a huge problem.
It's devastating because it changes the spark gap. Remember, this machine doesn't cut by touching. It uses an electrical spark across a microscopic gap.
And how small are we talking?
We are talking between 0.01 and 0.05 millimeters.
Wait, 0.01 millimeters, I can't even picture that. If the wire sags, that gap is gone.
Exactly. Or it becomes inconsistent. The electrical discharge goes wild. You don't get a clean, straight cut. You get a tapered, imperfect one.
And we can't forget the fluid, right? The machine is submerged in that dielectric fluid.
And it's just as sensitive. Temperature changes its viscosity, its conductivity. If it gets too hot, the sparking becomes unstable. You get a rougher surface finish. You lose that mirror-like quality WBDM is known for.
Okay, so heat is the invisible killer, silently warping the entire system. Let's switch gears. What about the enemy you can actually see?
The abrasive one, our second requirement, total cleanliness, the elimination of dust.
And the sources are really clear on this. Dust isn't just untidy. They call it, abrasive sandpaper.
That's the one. And it's not an exaggeration. Ignoring basic shop cleanliness will, without a doubt, destroy your positioning accuracy in a matter of months, not years, months.
And it's not just dust, right? It's a specific mixture.
That's the key. It's a combination of dust, oil from the machine, and tiny metal chips from the cutting process. These three things mix together on your most expensive parts, the ball screws, the linear guide rails, and they create a grinding paste.
A grinding paste. So every time the machine moves an axis.
It's not sliding smoothly. It's literally grinding itself down with this horrible abrasive sludge.
The statistic on this blew me away. The source said this contamination can reduce the life of your guide rails by 40 to 60%. Is that just from the abrasion?
Primarily, yes. You're introducing grit into a system designed for microscopic precision. It just eats away at the metal surfaces. You're basically cutting the life of these core components in half because of what? Poor air filtration.
And the loss of accuracy is just as bad. A new machine, we're talking a tolerance of plus or minus 0.01 millimeters, world-class stuff.
But after a year in a dirty shop, that abrasive wear creates slop in the system. The error jumps, often past plus or minus 0.03 millimeters.
And at that point, the machine can't do the job you bought it for.
Exactly.
Yeah.
You've turned your aerospace grade machine into one that can barely handle basic stamping dies.
And there's a secondary effect too, right? With the electronics, dust acts like a blanket.
It does. It settles on heat sinks, gets inside electrical cabinets, and it stops components from cooling down properly. Remember how important temperature stability is. Now you've trapped heat inside the electronics, risking burnout. It's a massive cost multiplier.
Okay, so we've got the invisible warping from heat and the abrasive grinding from dust. Let's move to the third pillar, the shaking truth of external vibration.
This is a classic factory mistake. You buy this ultra-precise machine, and you stick it 10 feet away from a 100-ton punch press.
Or right next to the main aisle where forklifts are driving by all day.
And the compromise is immediate. If the machine shakes, even on a microscopic level, that wire, that super thin, tightly stretched wire, it starts to oscillate.
And that oscillation is the death of surface quality.
Absolutely. The spark gap widens and narrows unpredictably. The discharge gets erratic. And the result on the part is visible defects we call chatter marks.
So those little ripple marks you see on a finished part might not be a software error. It could literally be the signature of a truck that drove past the building.
That's a perfect way to put it. And there's another effect here, debris flushing.
Okay, with that.
The cutting process melts tiny bits of metal inside the cut slot, which we call the kerf. That debris has to be flushed out by the fluid.
But if the machine is vibrating?
It disrupts the fluid flow. The debris doesn't get flushed. It stays, resolidifies, and creates these thick, rough layers we call recast layers. This is a huge problem. Recast layers create microcracks and severely weaken the finished part.
So you need to isolate the machine. But, I mean, digging a separate foundation for every single EDM sounds crazy expensive for a smaller shop. What's the practical fix?
That's a great question. The separate foundation is the gold standard, sure, especially if you have heavy stamping presses nearby. But the practical compromise is to use very high-quality vibration damping feet.
Not just some cheap rubber pads, I'm guessing.
Definitely not. These are engineered systems designed to absorb specific frequencies. And you have to put your EDMs in a dedicated part of the shop, far away from the heavy machinery. You isolate it from the floor if you can't isolate it from the earth.
And all that shaking, over time, it damages the machine itself. The source mentions something called stress relaxation.
Right. It's structural fatigue. Years of constant tiny vibrations can actually warp the machine's casting and loosen critical screws. You start chasing alignment problems that have nothing to do with calibration. It's just long-term environmental wear and tear.
Okay, let's wrap this up with our fourth and final pillar. The invisible threat of air quality and electrical protection. This seems to cover everything from health to humidity.
It does. We have to look at it from three angles. First is health and safety. The working fluid, that oil, it creates a mist and fumes under the heat of the spark.
And these particles are tiny, right? So they're easy to inhale.
Extremely. They're typically less than 5 microns, small enough to get deep into your lungs. Chronic exposure is a serious health risk. Not to mention, the oil settles on the floor and creates a massive slip hazard.
So what's the target for air quality? What should a shop aim for?
You want to keep the particulate levels really low. The standard is usually around 0.5 milligrams per cubic meter.
And the best way to do that?
Source capture. You need oil mist collectors right at the machine enclosure, catching the fumes before they ever get into the shop air. It's not optional. It's part of the system.
Okay, so that's the health side. But that same oil mist is an electronics killer.
It really is. It gets into electrical cabinets and coats everything. Circuit boards, connectors, it blocks heat dissipation, and if the oil has any conductive particles in it, it can cause short circuits. A catastrophic failure waiting to happen.
Which brings us to the final piece of this puzzle, humidity. The target, I read, is really specific. It has to be between 40 and 60%.
And that range is critical for two opposite reasons. If it's too dry, below 40%, you get static electricity, which can fry sensitive electronics.
And if it's too wet, above
The
60%?
rust, corrosion, and worst of all, condensation.
Condensation inside an electrical cabinet, that sounds bad.
It's a disaster, especially in humid climates. They call it sweating. Moisture forms inside the cabinets and shorts everything out. Motors, boards, wires, all gone. It's the ultimate invisible electrical threat.
The sources had a really practical checklist for this. What were the key takeaways?
It was very specific. First, seal your electrical cabinets with moisture-proof sponge gaskets. Second, use desiccants like silica gel inside the cabinets, and you have to change them regularly. And third, for machines that sit idle, you can apply a thin acrylic film to the circuit boards to protect them.
All right, let's bring this all together. A final checklist for the listener on these 4 pillars.
Okay, first, absolute temperature control. Lock your room at 20 Celsius, plus or minus 1 degree. Second, total cleanliness. You have to prevent that abrasive grinding paste that will cut your machine's life in half.
Right.
Third, vibration isolation. Whether it's a special foundation or just high-tech damping feet, keep that wire stable. And finally, manage your air. Control the oil mist and keep humidity between 40 and 60% to protect people and electronics.
And the value proposition is just crystal clear. This isn't about making the shop look nice. It's about protecting a multi-million-dollar asset. It's an investment that pays for itself in less maintenance and longer machine life.
Absolutely. You can't produce parts accurate to a few microns if your environment is out of control. We've just spent this whole time talking about how a tiny change in temperature can physically twist a massive iron frame, how a little bit of dust can grind down hardened steel.
It's incredible when you think about it on that scale.
It is. And it leaves you with a final thought to consider. If today's precision manufacturing requires this almost fanatical level of environmental stability just to function, what does that tell us about the future? Think about nanoscale manufacturing or advanced robotics. Systems where that kind of absolute stability has to be artificially created just for them to exist. That level of dependence on the environment is something to really think about.